Moment distribution method. Introduction. The moment distribution method is an approximate iterative technique for analyzing indeterminate beams and frames. Since it is closely related to the slope deflection method, in this lecture, I am going to show how we can arrive at the former from the latter. Once we establish a firm mathematical basis for the moment distribution method, we can then use it procedurally to quickly and accurately analyze beams and frames using hand calculations. Here, I am going to start with the slope deflection formulation for a continuous beam. I then show how the formulation can be viewed as a mathematical basis for the moment distribution method. If you are not familiar with the slope deflection method, please review lectures SA 27 through SA 33. Here is a continuous beam having two spans. It is subjected to a concentrated moment at B. Let's assume both beam segments share a constant EI. We begin by writing the slope deflection equations for the beam segments. Here are the equations for segment AB. And here they are for segment BC. The joint rotations, theta A, theta B, and theta C are unknown. To determine the rotations, we need to write three joint equilibrium equations. Isolating the beam's joints, we get these free body diagrams. Then, we can write the moment equilibrium equation for each joint like this. We can expand these equations like this. To analyze the beam using the slope deflection method, we need to solve equations 1, 2, and 3 simultaneously for the unknown rotations. If we did, we would get But solving these equations by hand is feasible when there are only a few of them. As the number of equations increases, however, it becomes more and more cumbersome to solve them without the use of the computer. This is where the moment distribution method comes in. It offers an approximate yet accurate way to solve these equations using hand calculations. So, let's see how this approximate technique works. Moment distribution is an iterative technique where in each iteration we calculate a part of the solution. Let's begin by transforming the slope deflection equations into a suitable form for our approximate analysis. We are going to rewrite the unknown joint rotations in the series form like this. In the expanded form, these series can be written as Then, we proceed to find the rotations in a stepwise manner, where in each step we calculate one term of a series. That is, we calculate theta A1 in step 1, theta B1 in step 2, theta C1 in step 3, theta A2 in step 4, theta B2 in step 5, and so on. We continue this process until we reach a point at which the computed values are very small and for all practical purposes can be ignored. Once we reach that point, we have the approximate rotations and member end moments for the beam. Let's go through the process and see how it works. Using the series notation, we can rewrite the slope deflection equations this way. To save space, I am going to shorten the notation like this. So, I only write one term of the series at a time. The terms further down the series are hidden in the three dots. Note that each equation consists of two main terms. For example, in this equation, we have a term associated with theta A and another term associated with theta B. Since the left-hand side of the equation represents a bending moment, then each of these terms must also be a bending moment. I am going to enclose each of these bending moment terms in curly brackets like this. This helps us remember that a member-end moment can be viewed as the sum of two moments, a moment due to the rotation at the left end of the beam segment and a moment due to the rotation at the right end of the segment. Then, the joint equilibrium equations can be written as Here is where the approximation comes into the picture. We are going to calculate theta A1 here, using equation 1. We use equation 2 to calculate theta B1. And we determine theta C1 using equation 3. So in step 1, we are going to use equation 1 to find theta A1. But since we do not yet have a value for theta B1, we assume it and the remaining terms in the series to be 0, so we can write the equation as solving for theta A1, we get 0. If we substitute this value in the slope deflection equations, we get or this term is the incremental bending moment at end A due to theta A1. It is the product of theta A1 and 4EI over L. Naturally, since theta A1 is 0, we end up with a 0 here. Also, this is the incremental bending moment at end B due to theta A1. So, we are done with the first iteration of the moment distribution method. Let us tabulate the incremental moment values, even though at this point they are 0. Here is the incremental moment at A, and here is the moment increment at B, both obtained from the slope deflection equations for segment AB. Before we perform the next iteration, we need to simplify the slope deflection equations by moving the computed incremental moment values outside the curly brackets, like this. In the second iteration, we are going to use the second equilibrium equation to calculate theta B1. Here is the equilibrium equation in the expanded form. Then, since we do not know any of the remaining terms in the series, we assume both theta A and theta C to be 0. This allows us to directly calculate theta B1 from the equation. Substituting this value in the most recent slope deflection equations, we get or note the incremental moments due to theta B1. This is the incremental moment at the left end of AB, and this is the moment increment at the right end of AB. This is the incremental moment at the left end of BC, and this is the moment increment at the right end of BC. Let's tabulate them. Before we get to the next step, we need to rearrange these equations by moving the calculated moment increment values outside the curly brackets, like this. In step 3, we use the third equilibrium equation to determine theta C1. Here is the equation in expanded form. Since we are calculating theta C1, we set theta B to 0. This gives us solving the equation for theta C1, we get substituting this in the most current version of the slope deflection equations, we get or here are the incremental moments for BC. This is the moment at the left end of the segment, and this is the moment at the right end of the segment. Let's add them to our table. Now, rearrange the slope deflection equations. By now, you may be telling yourself, this seems to be too much work. Why do we want to do all this when we can solve the equation simultaneously and get the answer rather quickly? My response would be, wait until we have our table completed. Then you will see how quickly we can analyze the beam using only hand calculations without writing a single equation. Back to our derivation. So far, we have completed 3 iterations. Now on to the next iteration. Going back to equilibrium equation 1, we can write, again, setting theta b to 0, we can solve for theta a2 like this. Substituting this value in the most recent version of the slope deflection equations, we get, or, here are the incremental moments for segment AB. Here is the moment at end A, and here is the moment at end B. Let's add them to our table. Now, rearrange the slope deflection equations. The next iteration deals with theta b2. Here is the second equilibrium equation in expanded form. Setting theta A and theta C to 0 and solving for theta B2, we get, substituting this in the slope deflection equations, we get, or, here are the incremental moments. Let's add them to the table. Now, rearrange the slope deflection equations. Next, we use the third equilibrium equation to calculate theta C2. Set theta b to 0 and solve for theta C2. Substitute this in the slope deflection equations to get the incremental moments for segment BC. Here is the incremental moment at end B, and here is the moment increment at end C. Add them to the table. Now rearrange these equations. Hopefully, you are beginning to see the iterative process of incrementally calculating the joint rotations and member end moments. Let's go through a few more iterations quickly. In iteration 7, we want to find theta A3. Here is the equilibrium equation. Setting theta b to 0 and solving for theta A3, we get, now we can write the slope deflection equations as, here are the incremental moments. Add them to the table. Now rearrange the equations. Iteration 8. We are now calculating theta B3. Here is the equilibrium equation. Set theta A and theta C to 0 and solve for theta B3. Substituting this value in the slope deflection equations, we get, updating the table, we get, now rearrange the slope deflection equations. Notice how the incremental moments are decreasing in magnitude in each step. This reduction in value continues as we continue calculating more and more terms in the series. We can stop this process when the computed incremental moment values are small enough to be ignored. Let's see the results of a few more iterations. The next iteration gives us these values. One more iteration and we get these values. Then we get these. And these. These, and these. Assuming that these moment values are small enough to be ignored, I'm going to stop at this point. Here are the slope deflection equations after this last iteration. The theta values that are being computed at this point are rather small, and are getting smaller and smaller with every passing iteration. This means that for all practical purposes, we can assume that the remaining terms in the series add up to 0. Therefore, the member end moments can be approximated as we can arrive at these values directly from our table by adding the incremental moments in each column. Summing the values in this column, we get m over 1024. Sum of the values in the second column gives us m over 2. We also get m over 2 by adding the values in the third column. And we get m over 1024 for the sum of the values in the last column. So, these approximate moment values constitute the results of the moment distribution method for analyzing the beam. Here's an interesting fact. When using the moment distribution method, we don't need to go through the equation manipulation process that I just went through. We can analyze the beam by generating this table without writing a single equation. I will further discuss the process of generating the moment distribution table in the next lecture. To wrap up this lecture, however, let me demonstrate the process with only a brief explanation. As I do this, keep your eyes on our existing table as well as on the table I'm about to create. They are identical in terms of the values being generated. We start by placing the applied moment at the top of one of these middle columns. I am going to place it here. According to the slope deflection sign convention, this represents a negative moment since it is acting in the counterclockwise direction at the joint. Now we are going to balance the moment at joint B. That is, we enforce moment equilibrium at the joint. To do so, we are going to negate the existing moment, then distribute it between the two sides of the joint. This is done in proportion to the relative rigidity of the two beam segments. Since in this example, both segments have the same EI over L ratio, the moment is going to be distributed equally between the two columns. So we write m over 2 here and m over 2 here. Notice that now sum of the moments at B is 0. We say that the joint has been balanced. Then we carry half of this moment over to the other end of the member. That is, we write m over 4 here. And half of this moment carries over to the other side of BC. We write m over 4 here. Now we balance the moment at this joint. This means we add a negative moment of m over 4 to this column. As a consequence of adding a new moment value to the table, half of the value carries over to the other side of the member. So we write negative m over 8 here. Similarly, we first balance the moment at this joint, then carry half of the balancing moment over to the other side of the member. Back to the middle joint, we balance the total moment at the joint by adding these moment values, which half of each is a carryover moment. This gives us now balance joint A, then carry over half of the balancing moment to the other side. Balance joint C, then carry over half of the balancing moment to the other side. Back to joint B, balance the joint and carry over half of the balancing moments to joints A and C. This process continues until we are satisfied with the accuracy of the results, until the moment values become small enough to be ignored. Once we are done with this iterative process, we add up the moment values in each column. That gives us the member end moments for the two segments. Then we can determine the remaining member forces and support reactions by applying the static equilibrium equations to each segment, like this. Now that we have a better understanding of the mathematical basis of the moment distribution method, we can apply the technique procedurally to analyze indeterminate beams and frames. We'll continue this discussion in the next lecture.